これがウォードップのイントロです。ご視聴ありがとうございます。チャンネル登録も忘れずに。
Hi everyone. Today I want to explain what people sometimes call the equation of the universe. Well, there isn't literally one single equation that explains everything. But if you ask physicists what the closest thing is, many of them will mention Einstein's field equation, because it basically describes how gravity works in the universe. And what's cool is that once you understand what each part means, it's actually not as scary as it looks. This over here is the equation. So before we even talk about the symbols, here's the main idea. This equation connects two things. One, the shape of space-time, and two, the matter and energy inside space-time. And it basically says matter and energy determine how space-time bends. And that bending is what we experience as gravity. Anyways, so what is space-time? We need to understand one concept. Space-time is basically the combination of 3 dimensions of space and 1 dimension of time. Instead of treating space and time as separate things, Einstein treated them like one connected system. So the universe is not just objects moving in space, it's objects moving through space-time. Before Einstein, people thought gravity was like an invisible pulling force, but Einstein's idea was very different. Gravity is not really a force. Gravity is the result of space-time being curved. So if you put a massive object in the middle somewhere, like a planet or a star, space-time bends around it. And then other objects like moons or light naturally follow that curve. That's why planets orbit the sun. That's insane. Not because the sun is pulling them like a rope, but because space-time around the sun is curved. So now we're going to split the equation, left side, and this is the right side. The easiest way to understand this equation is to treat it like a balance. The left side describes space-time itself, the geometry, and the right side describes what's inside space-time, matter and energy. So the equation is basically saying the geometry of space-time depends on the energy inside it. Let's start with this part right here. Pronunciation is Gμν. This is called the Einstein Tensor. We don't really need to remember the name. The important part is what it represents. It represents the curvature of space-time. In other words, it describes how much space-time is bending at a point. If space-time is flat, the term is small. If space-time is strongly curved, like near a black hole, this term becomes huge. So you can think of Gμν as how warped is space-time. We add this term. The pronunciation lambda Gμν. This is the part connected to the expansion of the universe. Lambda is called the cosmological constant. The simplest way to think about it is even empty space might contain energy, and that energy can cause space-time to expand. This is related to what we call dark energy. So cool! Anyways, which is one reason the universe is expanding faster over time. So this term is basically even empty space affects gravity. Now the right side, as you know, is Tμν. Now the right side contains Tμν. Pronunciation is Tμν, obviously. This is called the stress energy tensor. This represents all the matter and energy in a region, not just mass. It includes things like mass density, like how much matter is there, energy density, pressure, movement of matter, radiation, like light. So Tμν is basically what is inside the universe at that point. Sorry, I'm about to have lunch, so excuse me. Berry right here. It's really good. It's good. Anyways, it includes things like mass density, like how much matter is there, energy density, pressure, movement of matter, radiation, like light. So T, nu, is basically what is inside the universe at this point. Now we have this factor, a pi g over c to the fourth. This part is mostly a scaling constant that makes the equation work correctly. So let's break it down. G is the gravitational constant, Newton's constant. C is the speed of light, and c to the power of 4. This whole fraction basically connects the units of energy and matter to space-time curvature. This is like a conversation factor between physics and geometry. Equation again. So now we can translate it into plain language. Left side describes how space-time is shaped. Right side describes how matter and energy are present. So the equation says matter and energy determine the curvature of space-time, and curved space-time determines how matter moves. That's the main meaning. So here's a simple example. Earth has mass, so Earth bends space-time around it. And because space-time is curved, objects fall towards Earth. So when you drop something, it's not being pulled by a magical force. It's simply following the curved geometry of space-time, even though we still call it gravity. Bend and snatch. So here's another example. Light has no mass, obviously. So in Newton's theory, light shouldn't be affected by gravity much. But Einstein's equation predicts that light follows curved space-time. So when light passes a star or a black hole, it bends. And astronomers actually observe this effect in space. It's called gravitational lensing. That's one of those reasons Einstein's theory became famous. That's so cool. That's so cool. So this equation is basically the foundation of modern cosmology. Using this equation, scientists can describe black holes, the expansion of the universe, gravitational waves, time slowing down, your strong gravity, like, for example, GPS satellites have to correct for relativity because time moves slightly different in orbit compared to Earth. So this isn't just theoretical. It literally affects modern technology. So, one important thing though, Einstein's equation is incredibly accurate for large objects like planets, stars, and galaxies. But it doesn't fully work when we go extremely small, like quantum particles. So scientists still don't have a complete theory that combines gravity and quantum mechanics. That's why people say physics still is missing the final equation. So that's Einstein's field equations. If you understand the big idea, it's actually pretty simple. Space-time has a shape. Matter and energy influence that shape, and that shape influences how everyone moves, how everything moves. That's basically the modern understanding of gravity. If you want, in the next video, I could explain something related like the Schwarzschild, like black hole equation, gravitational waves, or the three-body problem. So yeah, don't forget to subscribe and turn on the notification bell. Thank you for watching. Until next time.